Suppose you have quantitative data in one variable and you want to see if your data are approximately normally distributed. In any data set, the data will not be exactly normally distributed in any real-world situation. But approximately normally distributed is maybe a goal that we could achieve. Under ideal conditions, the histogram or stem plot of the data would be single-peaked, symmetric, and bell-shaped. The data would conform to the 68, 95, 99.7% rule, and a normal probability plot of the data will be linear. So again, these are ideal conditions, and in real-world situations, they're not going to be perfectly met, but you might be able to make a judgment call that your data are approximately normally distributed if these are close to being met. Here is an example. We've got 38 students taking a 100-point unit test, and these are the scores that they earned in points, and we want to know if these scores are approximately normally distributed. Well, according to this list right up here, the first thing we should do is check a histogram or stem plot of the data to look somewhat like a bell curve, and then we'll check the 68, 95, 99.7% rule, and then we'll look at a normal probability plot of the data. So here is a stem plot of the scores, and as you can see, it's single peak, symmetric, and somewhat bell-shaped. The mean of this distribution of scores is 78.9 points. The median is 78.5 points. The mean and the median are nearly equal, which is consistent with the symmetry of the distribution. The standard deviation is 11.8 points, and the interquartile range is 17 points. The data contain no outliers because all of the data values are within the fences of 45.5 points and 113.5 points. So far so good. We have a distribution that looks approximately like a normal distribution. Now let's check the 68, 95, 99.7% rule. What I did was I broke up the data into intervals. I took one interval that consisted of, that went from X bar to one standard deviation on either side of it. So we have X bar plus S, plus or minus S, X bar plus or minus 2S, and X bar plus or minus 3S. And we want to see what proportion of all the data values fall within each of these intervals. Now, if you use the mean of 78.9 points and the standard deviation of 11.8 points, the boundaries of this first interval are 67.1 points and 90.7 points. And in that interval, I counted 22 scores. 22 out of 38 is 58%. Now that's somewhat less than 68%, so maybe this is a departure from normality. This is not really as high a percentage as we'd like to see in that middle interval. Okay, the next interval, which is a little wider, is one standard deviation wider, extends from 55.3 to 102.5. Again, we took X bar, 78.9, and we subtracted 2 times the standard deviation of 11.8. And we added 2 times the standard deviation of 11.8. In that interval, we have 37 of our 38 observations, which is 97%, and that's just slightly above 95%. So maybe getting better. And then in the interval from X bar to X bar minus 3S and X bar plus 3S, which is 43.5 and 114.3, we have 38, or all of our observations. 38 out of 38 is 100%, which is approximately 99.7%. So in this little breakdown right here, we have fewer observations in the middle of the distribution than we would expect if the data were approximately normal. But then in the other intervals, things conform to the 68, 95, 99.7% rule much better. Now we want to look at a normal probability plot. And when you make a normal probability plot, this is something you're going to want to do on your calculator because it's way too hard to do by hand. Okay, so what you want to do is take out your calculator and put your data into a list. So I put my data in list 1 right here, and they're in the same order that they were listed on the previous page. I'm going to do one variable stats on this list, and this is where I get my mean of 78.9 and my standard deviation of 11.8. Okay, now if I want to make a normal probability plot, what I do is I go to second y equals, that's the stat plot menu, and I go in there and I select one of them. I'm going to turn plot 1 on. Now as you can see right here on the type line, it's set up right now to be a modified box plot. If I want a normal probability plot, I need to select this one right here. So I'm going to go to the end of that list right there, and I'm going to select that one. And then when I do that, it asks me where are my data. Well, my data are in list 1. Then it says which axis of the plot do I want to put the data values on. And I usually use the x-axis, but it really doesn't matter. The plot should look approximately linear either way, okay, if the data are normally distributed. Okay, and then we can just quit out of here and go zoom 9, and the calculator will make the normal probability plot for you. Now, as you can see in this plot, it's not exactly linear. There's some deviations from linearity over here and a little bit over here. Okay, in an ideal situation where you have normally distributed data, this normal probability plot will be a straight line. But in real world situations, when you're working with actual data, there are always going to be some slight variations or deviations from normality. And you see some of them here and some of them there. Okay, but ideally this normal probability plot should look linear. Okay, so what's the bottom line? Well, we have a stem plot which is single peak symmetric and somewhat bell-shaped. That's plus. The data don't quite conform to the 68, 95, 99.7% rule because we didn't have enough observations in the middle interval of x bar minus s and x bar plus s. And the normal probability plot is not quite linear. So my conclusion is that the distribution of test scores is almost but not quite normal. We have a slight deviation from normality as far as that count in that interval went, and other than that, things look pretty good. So in this situation, I would say, well, they're close to normal, but not quite.